Good morning and welcome to our webinar for this morning. Today we'll talk about the AC meter card. This is a new expansion card for the OrionMX, and there you see it in the top slot of the 2S expansion case for the OrionMX. This morning I'll be one of your presenters. I'm Ray Wright. And I'm here with Saurabh Rajpal, our senior sales engineer, and Joe Bowden, senior systems engineer, who has worked on some source transfer applications, which we'll talk about today. The agenda, we'll talk about some of the features of the meter card, then move on to applications, configuration, and we'll show you how it appears in the quoting card. Meter card is a marriage between Bytronics instrumentation and OrionMX. We repackage the Bytronics PowerPlex. The PowerPlex is very much like a panel meter, like a 50 or 60 series panel meter, but it has some additional capability where it can actually measure the voltages on two buses and the currents on one line. Gives us more flexibility in some applications that we'll talk about. And you understand how Bytronics instruments work. There's AC analog inputs and measurements are made based upon basically three-phase currents and three-phase voltages. Hundreds of values are derived from there, power measurements, energy measurements, etc. So we repackage that, and there is an optional display that you can put on there. We repackage that into a card that fits into the OrionMX. Here's what the card looks like. The 3 PT inputs from bus 1 and bus 2, and 3 split core auxiliary CT inputs from line 1. And we use the term auxiliary in that that implies that it's connected over the existing CT circuit, which would nominally be 5 amps. Bring in the C1 card. C1 card was developed to bring additional measured quantities into the system, notably a measured neutral from line 1 and also a measured neutral from line 2, along with the phase ABC amps coming in on split cord for the line 2. So what you see there is gives you a full set of measurements, ABC and neutral on your currents, ABC on your potentials. And there is an additional output on there. That's for future use. We see some future higher speed control applications where the output will need to be closed, typically for breaker operation, in response to some changing AC analog input condition, like frequency or synchronicity. But that's for the future. Talked about the split core CT. This is, again, an auxiliary CT. It clamps to the existing CT circuit. It's a precise 1,000 to 1 transformer, essentially. And nominally, the circuit would be 5 amp that we clamp around, so that would be converted to 5 milliamp. It does have a very high dynamic range and can go all the way up to 100 milliamp output in the presence of a 100 amp signal, which would be typically seen for a high fault condition. This is a calibrated system that we provide. So we actually calibrate the meter card to the split core CT for phase A, B, C, and neutral. And what this does is it enables us to maintain the same accuracy using the split core CT that we would quote for hardwired CTs and PTs in the Bytronics instrumentation. Bytronics instrumentation, they're known for very high precision and high measurement accuracy and fast measurements. The AC power measurements available to the Orion are detailed there. The ones that are highlighted are the ones that we'll talk about a little bit more in the application. The measured quantities, the full scope of amps, volts, watts, bars, frequency, energy, that kind of stuff, plus a few extra things. As you see highlighted there, we have a 51 fault pickup, we got phase angle volts, and the slip frequency volts between A and B, or between lines 1 and 2, or buses 1 and 2. That gives us an idea of whether we can close two sources in on each other, whether they're in sync or not. See what these look like in the case. There's one M1 meter card in the case. That's good for monitoring three-phase voltages on two buses, or three-phase voltages and currents on one circuit. And you can put two of those into a 2S case. And next click. This is a combination of the M1 and C1 card, as we mentioned before, three-phase voltages and currents, and a monitored measured neutral on two circuits. We have a larger case in the 4S expansion case, and you can put between 1 and 4 M1 meter cards in the 4S case. This shows combination of 3 meter cards and 1 IO expansion card. This again would measure three-phase voltages and currents on 3 circuits. It also could control open close on 3 breakers or switches, or monitor the positions of 3 breakers and switches. And one reason we put this in here is that this is going to be one of the first applications we talk about, how to add this type of automation to a legacy substation. We also want to emphasize that there is an optional display that can be provided. This is the D650 Bytronics display. This is actually a DNP or Modbus client. So the display itself can query any IED, including the Orion, and any data value inside the Orion can be read by the display, scaled and displayed as shown. You may ask, what does the meter card bring to the Orion in general? Well, it really brings more intelligence into restoration schemes. We are using the Orion in more schemes for reclosing and tying in tie breakers, and adding some intelligence to that is important. For instance, checking for presence or absence of potential directly, rather than asking for those values from an IED. Similarly, the demand amps, the value that comes into the meter card, very handy in determining what pre-load or pre-fault conditions are on the line, and also check sources for synchronicity when we're closing tie breakers and doing other operations. So we can be a little bit more intelligent in an easier way by bringing these values in directly. We also can bring intelligence into isolation schemes. We use the Orion in Flisser schemes, and being able to pick up on an overcurrent condition is handy. Those fault pickups can be used by the Flisser controller to determine the location of the fault along the feeder. And then we have now better options to replace legacy hardware, and that's the first thing we'll talk about here. So we talk about 5 applications. The first is adding automation, adding SCADA to legacy distribution substations that don't have any automation. We'll talk about a upgrade of older transducers, smarter tiebreaker control, a better Flisser solution. Actually, I should say an alternate lower cost Flisser solution, and this ACOD automatic changeover device solution source transfer. This is a packaged system from our NovaTech systems operation. Start with this one here. This is a substation from a customer down in Texas. A lot of these smaller distribution subs don't have any automation. They may have old reclosers in them. Some of our Midwest customers have some of these old Kyle reclosers. Don't have SCADA in those substations, those old oil reclosers. Some of these older subs have still electromechanical relays. And the question is, how can you add automation easily without taking an outage? So we'll look at that circuit there, breaker 40, and the electromechanical relay, hypothetically, that could be in that substation. We could say it could be connected in there like that. We have 5 amp nominal CT circuits coming into the electromechanical relay. Of course, there'd be an output to the breaker. So the first thing we would do is add in the meter card with the Orion. And there you see the split core CTs, 1000 to 1, converting the 5 amp nominal to 5 milliamp. And that is a very simple, straightforward way of adding automation. Of course, you don't have to take an outage to put those split core CTs on there. So what would that give you? It would give you demand amps, fault pickup, plus anything related to current. I think demand amps would be valuable for your planners to see how your loading was changing on that line over time during holidays. Maybe look at transformer loading, that kind of thing. So the next thing you'd consider is adding in some of your voltages. So this is a typical 4-wire, 3-element Y-connected system. So those 3 voltages come in and they actually land just as shown in the diagram. And so now you have a full set of power measurements. You have watts, bars, things like that, energy values, all kinds of things. So this gives you the full set of power. And then the next logical step would be to add in some discrete I/O so you could check for breaker status and also send down breaker open and close. So now we have automated this circuit. We provided SCADA onto this circuit, and you could do this for the other 2 circuits in the substation. And the next slide, that's pretty much what this would look like. You would only need 1 expansion card for I/O, and then you'd probably use some of the I/O that's built into the OrionMX, and 3 M1 meter cards could actually look at all of what you need on those 3 circuits, breaker 40, 30, and 20. So again, this is an easy way to add SCADA without taking an outage in a small, simple legacy substation. We talked about the definite time over current element. This is a 51 definite time. It's set in NCD. You can set your pickup threshold in amps and the duration. There is some hysteresis built into that, makes 3%, so that after you pick up, if you would drop slightly, you don't keep picking up and dropping out. The enunciation of a pickup is in these points. These are inputs that you can read from the meter card, and you can see the binary input there indicating that you picked up on phase A, B, and C. There also is an output to reset the relay element. Here's a legacy transducer. You've probably seen some of these old scientific Columbus AC to milliamp transducers. They're still out there, lesser than there were, but you know how they work. 120 volt or 5 amp nominally from PTs and CTs being converted down to milliamp quantities, and then those milliamp quantities are input to a legacy RTU, which in turn goes to SCADA. You see something like this, you could alternatively go with a much simpler solution that looks like that. That solution below would be able to do what many of the legacy solutions like the above would be able to do. The next application we'll talk about is smarter tiebreaker control. The simple parallel substation there with a normally open tiebreaker, source 1, source 2. For the purpose of this discussion, we will assume that there are potentially some scenarios where source 1 and source 2 should not be tied to each other. We'll assume that sometimes they're in sync, sometimes they're not in sync. We'll also assume that under certain loading conditions, different times of the day, different times of the year, it might be impossible for source 2 to pick up the full load of the 6 feeders, or for transformer B to pick up the full load of those 6 feeders. So In this case, we'll have to do a load check to make sure that transformer B or source 2 won't be overloaded when picking up the extra load on feeders 1, 2, and 3. We'll go through that animation in just a second. We'll also, again, talk about checking for sync of sources 1 and 2. So first step, lose source 1 and lines 1, 2, and 3 go dead. Orion senses that loss. Orion checks the pre-loss load on feeders 1, 2, and 3. It compares to limits for source 2 and transformer B, and we'll also check for other safety and operational interlocks. We would think demand amps would be a good thing to check. You could check demand amps for the last 15 minutes or set your interval longer. You could set that for several hours to make sure that the highest amount of current that would be experienced on those feeders would be able to be handled after you close that tiebreaker. And so once you check that, you can close the tiebreaker, open switch A. Yeah, so now we have source 2, transformer B, feeding all 3 lines over on that left side, plus the 4, 5, and 6. So now we're in the scenario where source 2, obviously, and transformer B more heavily loaded. And the next step is we can expect source 1 to come back at some point. So when source 1 returns, Orion would check the synchronicity with source 2. So you'd say, is there any angle between the sources? Is there any slip frequency? Is there any significant voltage difference? And if not, close the switch, then open the tiebreaker. We're back to normal. Now, the next scenario, click. If the sources are not in sync, Orion would open the tiebreaker first and then close the switch. Now we're back to normal. In this situation where the sources were not in sync. We're back to normal without ever putting the 2 sources against each other. We mentioned demand amps. These are values that you can read from the meter card. Fairly simple. Again, you can set the demand interval as long as you want. And there is a reset on your demand amps as well. The next application we'll talk about is a Flisser solution. We've done a number of Flisser solutions, and now with the Orion and the meter card, with the ability to pick up on overcurrent faults, it gives us an alternative. And Saurabh Rajpal will describe this application. He'll first talk about how we've done it historically, and then he'll talk about the alternative with the OrionMX and the meter card, and I'll go through some animation.
Thank you, Ray. That was great. I'm Saurabh, one of the sales engineers at NovaTech. I'll be covering Flisser. Flisser stands for Fault Location Isolation and Service Restoration. In this example, how we've done historically, this distribution line spans over 36 miles through a rural area, featuring overhead distribution feeders. At the substation, we have a Flisser controller with the DA logic, which acts as a major Flisser controller that's talking over radio to various different vendors, reclosers, and switches. The idea here is Orion will isolate the faulted line section and restore service to the unfaulted section. As you can see, the feeder 6 is feeding various different loads and is able to talk over radio or fiber, whatever communication medium you use, and is able to limit the time, generally reduce the time to cut through the overall Flisser scheme and isolate the fault and restore as quickly as possible. That's the overall Flisser concept, and this is how it's been done historically. What we're proposing an alternative approach here, we can imagine you have a substation with similar line, a rural station with switches a motor operated disconnect switches. Here we're demonstrating M1, M2, M3 as 3 motor operated disconnect switch, and then M4 being the tie switch, which is also feeding in from an alternate source in case the feed from feeder 6 goes bad or anything, there's an outage between this line, an alternate source can come in and play the role there. So this method is relatively cost effective than adding reclosers. Of course, it won't have all the capabilities of reclosers, but now you've got automation. Now you can sense the data, the metering data, and also do the controls based on your Flizzr scheme that you have. So now we're going to take a look at an example if a fault happens on a distribution line, and how would a Flizzr controller, isolate the fault and sectionalize the fault. So here we have similar concept. We have the Flizzr controller at the sub, and it's talking a radio constantly to M1, M2, M3, M4, and similarly they have an alternate source that's coming in, which is the tie switch is normally open. What happens here is it's able to monitor the overcurrent faults, report demand amps, and also monitor and control each individual switches. So what happens if a fault occurs somewhere in this line? The M1 will pick up the fault and report it to the Flizzr controller, right? And this topology, the fault's picked up only at M1 and not M2 and M3. So we can assume that the fault is probably between M1 and M2. And what would that trigger would be the substation breaker will open and goes to a lockout state after attempting a number of reclosing attempts. Once that is done, we know there's a faulted section between the section 2. Excuse me. The Flizzr controller will determine then which line pick up on the fault. As you can see, the M1 is reporting a fault pickup, and the M2 and M3, there is no fault pickup. So now we want to isolate the faulted section to the unfaulted section, right? So in that case, the Flizzr controller isolates the faulted section by opening M1 and M2, and then it calculates the pre-fault demands and amps from the unfaulted section to see if the load can be picked up from an alternate source. If that is the case, if load can be picked up by an alternate source, the Flizzr controller at the substation will close the tie switch and the substation breaker, so we can have the service back on for the section 3, 4, and section 1. So all the customers that are not being impacted by the faulted section can restore the service, and that minimizes the overall impact of the fault. Once the isolated fault section is there, the crew will then go out and repair the line over there, and then clear the fault and return to normal operation. The tie switch at M4 will be open, and it's back to normal. This is a very simple example of Flizzr scheme. However, there might be different topologies that you may have, and we would be more than happy to work with you to work on a Flizzr scheme for your distribution automation scheme. Next we have is another application called source transfer. We call this a product called ACOD, stands for Automation Changeover Device. It's a built-in logic with software option 107. When you order a part for ACOD, you choose software option 107. The purpose of this is that you can automatically transfer from one source to another. It provides various flexibility in various scenarios that are baked in. It's an overall package solution. It comes with an embedded logic for 6 different modes that we'll cover in later slides. It has the battery power supply and UPS, including display or HMI, and it's overall a complete package. Now let's take a look at how the current ACOD looks like and how it works. So the current source transfer application, you can see there's a preferred source with a normally closed switch, and then an alternate source with normally open switch. It's exchanging inputs, outputs, and controls with an I/O, and that's feeding in to Orion LXM over comms. And then the PTs are being sensed with a PowerPlex meter. So you can see there is the current design was it has 3 peripherals, I/O, LXM, and PowerPlex. We're trying to enhance this and make less devices and do the same, if not better. The new design would look something like this. Now what you can do is you can, PowerPlex goes out of the picture because you can now sense the voltage with the MX, with the AC metering card, and all the input outputs can also get the statuses from the switches directly to the MX. For those of the application, if we need more I/O, we can always put more I/Os in the 4S chassis. So there is that option there. Let's take a look at the logic. The ACOD logic resides embedded in the Orion firmware, but we are working, and our system groups can convert the embedded ACOD logic to a Lua program or a 61131 logic to cater some of the special schemes that you may have for source transfer. In terms of HMI, we currently have push buttons that does the control, such as local, remote, manual, auto, lights to signify a loss of potential. There are selector switches and a small number pad display that shows you a very simple single line. And what we're doing is we're moving to making that a lot simpler with local lights and selector switches. And we're also giving the capability to provide a web page that can be used by your engineering and SCADA group to remote into the OrionMX using our Inkscape software. The next screen here, ACOD, is going to be presented by one of my colleagues, Joe Bowden. He's a subject matter expert. He's worked on ACOD significantly. He's going to go through what changes are we going through the drawings, and also go through various modes that it supports. Over to you, Joe.
Thank you, Saurabh. Yeah, as Saurabh mentioned, I've been involved in the design and support of the ACOD product, and I'll be also involved in implementing the updated design as well that it was discussed. So first, just wanted to look at its design, and as Saurabh mentioned a little bit later, we'll be going through its different operating modes and configurations. So on this slide that we're looking at here, we're comparing the control panel of the existing ACOD on the right with the proposed redesign on the left. This is what you would see if you were to open the cabinet door to an ACOD. So you can see in the existing design, not only are there plates with the selector switches and indicator lights for all the different modes, we've also got cutouts for the DDIOs there at the bottom, and a keypad to access the ACOD configuration. You can see on the top left with the blue and white buttons. This all fit on a panel that is in a custom 36 by 30 inch enclosure. As was shown on the previous slide, this uses different components for each of those functions. The Bitronics PowerPlex 2 meter is there for the PT connections, and then DDIOs provide all the I/O, and an Orion LXM as the head unit. For the consideration of a modern redesign, we've already seen that the OrionMX with the AC meter card and I/O cards can really simplify the devices down needed that are in the system. That takes out the DDIOs because we don't need separate I/O devices anymore, and then also deleting the keypad that would be there and moving that ACOD configuration to an HMI screen means that we can pare down to just the necessary selector switches and indicator lights on the control panel. That brings it down so we can actually fit this now into on a panel in a common 24 by 24 inch enclosure. On that control panel, looking at the updated design on the left, top left, we have the auto manual control and indicator lights. This allows you to enable and disable the ACOD logic for running. Next to that, we got the local supervisory control and lights to enable or lock out remote operation of the ACOD. That way it can be worked safely by a local technician. On the previous design, Those indicator lights are shown on the black panels on the top right, and the controls for them are actually buttons on the keypad. The last panel on the top is switch failure lockout indicator lamps. That's the same as the blue panel on the right. A lockout could be caused by a switch failing to operate. That could be due to either a fault on the line or to a mechanical issue with the switch. If a lockout does happen, blue lights are turned on, left for source 1, right for source 2. Then, I said, ACOD will not close in on a source that's been locked out. And then operator would need to disable ACOD and then correct what needs to be corrected, also switch it to local mode so that the operator can use the reset button to clear the lockout and be able to return ACOD to normal operation. The 3 bottom panels and the gray panels that you see there on the right are the same for both. These are these indicate the position and also allow for manual control of the switches that ACOD is connected to. The left is for source 1, the right's for source 2, and the bus tie control and indicator lights are in the middle. There's also extra lamps on those, the white lamps. Those indicate the potential for each source, because ACOD is hooked up to PTs and it's just monitoring voltage. The green and red lamps shown are indicating the position of the switches, open or closed. And as mentioned, if the ACOD is in manual mode and in local, then an operator is able to change the position of the switches and operate the switches with the controls there. Okay, next slide, please. So in that updated design in that 24 by 24 inch enclosure we're talking about, this is what the equipment layout would look like on the back panel if you were to open up the control panels. This is the brains of the operation. Highlighted, we have the major components of an ACOD. So that would be the MX shown in the maximum 4S chassis. There, it could be a panel mounted Ethernet switch. Below that is a power supply and battery backup system, as well as a heater on the left for outdoor installation. Other components that aren't highlighted here, but you can see there's an AC outlet for convenience, and then on the far right are the fuses and terminal blocks needed for connections to power, the PT, and IO connections. Next slide, please. All right, next I'd like to go over the modes that ACOD can be configured for. The 6 possible modes are shown here in this table. The highlighted ones, 1, 2, 4, and 5, do not utilize a bus tie. So therefore, it's one source operating at a time. To the right is a one-line diagram demonstrating what this implementation would look like. Modes 1 and 4 use source 1 as the preferred source, and therefore source 2 is the alternate. And then 2 and 5 modes have source 2 as the preferred, whereas source 1 would be the alternate. And we'll go into a little bit more on those a little bit later. Here we have modes 3 and 6 highlighted. These are both dual source, and they do utilize a bus tie. You can see that the diagram, the one line has changed there. This is similar as what Ray was discussing in his section about the tiebreaker control. So since that's already been discussed, we'll go back and we'll focus on the other modes 1, 2, 4, and 5. So let's see, starting in mode 1, source 1 is your preferred source, source 2 is the alternate. In the graphic here, the switch for source 1 is closed, depicted as red, and source 2 is open, green. And these are going to be the normal positions when operating in this mode. If potential is lost on source 1, that switch is going to be opened, and then the switch on source 2 will be closed. And now ACOD has transferred to its alternate source. This mode is called hold, because once ACOD switches to the alternate source, it will not transfer back to its preferred source, even if the potential returns there. So in order for it to be able to return to its normal operating mode, ACOD would need to be disabled using the auto manual switch, and then have the switch positions changed manually. That can be done either using those controls on the front while it's in local mode, or there are controls available to SCADA that those could be changed remotely and bring ACOD back on once it's in its normal position. Mode 2 basically follows the same logic as mode 1, but it's using source 2 as the preferred, while source 1 is the alternate. So again, if potential is lost on source 2, that switch is opened, and then the switch for source 1 will close. And this is also a hold type, so even if potential is returned back on source 2, ACOD still will not switch automatically, and that will need to be corrected by an operator. Going down to the other two modes, modes 4 and 5, things do get a little bit more interesting here. Mode 4 is similar to mode 1 in that source 1 is the preferred. So switch 1 starts out closed, switch 2 starts out open. If potential is lost on source 1, ACOD will go through the same steps to transfer off of source 1 to source 2, closing in on source 2. And now ACOD is monitoring and waiting for that potential to return back on source 1, because it does want to switch back. So once it sees that the potential has returned and all the criteria has been met, then it will go ahead and return back by opening source 2, closing back on source 1, and being back in its normal operating mode. And then for mode 5, it follows through the same thing, with source 2 being the preferred. It will go through the same steps if potential is lost, transferring over to source 1. And while it's operating on the alternate, source 1, it is monitoring to see if potential returns back. And if it does, and it meets the criteria, it will switch back to source 2 as the preferred. Okay. So wanted to give a little bit about actually doing the configuring of the parameters that ACOD logic is going to be following. And this is what you would see in the NCD screen, looking at the ACOD logic. You have an option for a descriptor for both source 1, source 2, and also actually the bus tie down there as well. In the existing design, these names would show up on the little screen that's on the keypad there. And otherwise, they could be on the HMI screen for the updated design. Below that, we have the LOP filter. That means loss of potential filter. This is a time window that we are assigning it to say, I want to make sure that the ACOD is considering potential for this long before operating. This is going to be paired with the cutoff and the return fields that are next. The cutoff is for ACOD recognizing if there is a loss of potential. This is 80%. So if it drops by below 80% of the nominal voltage, then it needs to be have done that for half a second, for 500 milliseconds, for it to consider it a loss of potential and operate on that. For the return, it's looking for 90% of the nominal voltage, at least 90% of the nominal voltage to return before it considers it a return of potential, again, for that 500 millisecond window before it recognizes it and will operate on that. Then we have the charge time set for 2000 milliseconds in this example. This is looking at the actual switch that's doing the operating here for source 1. You're giving it a time window to operate. If this is a slower switch, maybe you need to give it a little bit more time for ACOD to be able to recognize that it's changed positions from open to close or close to open. This is where that switch failure also comes into play. We have the same settings for source 2, so that way you can configure each switch independently of each other in case they are different hardware and they have different specifications you need to follow. Okay, next slide, please. And ACOD can run independently as it's a complete package, but also it can report to SCADA. And this is a set of points that you could expect to see on the DNP server port going up to a SCADA system or whatever you may have. So there could be the voltages for each of the phases for each source 1 and source 2. Below that, we have the loss of potential points that we were talking about. If ACOD recognizes there's a loss of potential, then those alarms would be tripped. Below that, we have the switch statuses, 89A for each of the field switches. Switch 1 is for source 1, switch 2 is for source 2, switch 3 is the bus tie. Then we have the state of the auto manual and local remote of the ACOD. Below that, the switch not able to operate. This is the switch failure that we were talking about for switch 1 and switch 2. And then also for that battery backup system, there's a couple alarm points that we're monitoring for that as well. Under voltage, or if battery low, also could be that the battery needs maintenance, maybe the battery needs to be replaced. If the ACOD is in manual, but it's in supervisory or remote settings, then controls can come from SCADA through the ACOD to the switches so that they can be operated remotely. And down there showing the 2 output controls that we would be using for those. Okay, at this point, I'm going to give it back over to Saurabh to finish discussing parts of the meter card.
Thank you, Joe. That was very informative. Thanks for that. So now we've looked at the applications, the various applications for OrionMX. I'm going to just go through how to configure the meter card in NCD. So the online meter configuration internally is, what it does is Orion internally pulls the meter card with DNP. The points are available for DNP and can be mapped to a DNP server for SCADA monitoring and control purposes. Let's take a look how that can be done. It's still the same software, no additional software is required. You would go on NCD, select the OrionMX. I'm using 2S for my example. So I would select 2S. In case you're going with 4S, you would select that and hit OK. From there, you would go to Configure tab and then go to the Hardware I/O and select the AC meter card. From there, you would add a new card. So if you've got, it'll give you an option to select card A or B. So I'm choosing card A, and at the bottom of it, you could see I'll choose NovaTech, and then I'm choosing the M1 meter card, which gives us the 6 PT and 3 CT with split core. Similarly, the same process can be repeated for card B, either if it's the same or you want to use the M1C1 card. After that's done, we would go into the meter input configuration. The input configuration by default is 3-element. It can be chosen by drop-down structure to either 3, 2, or 2.5, depending on how you're wiring. It's a Y or a delta. It allows users to configure their PT and CT ratio. For illustration purposes, I have PT ratios being set to 120:1 and CT ratio being 1,000 amps to 5 amps. Also, the user can configure the demand intervals. The amp demand intervals is 900 seconds, equivalent to 15-minute interval. You can change it to whatever your use case is, and 1 minute for the volt and the power average interval on the demand intervals. User can also set up the overcurrent monitoring. I've set up to 1,025 amps, so anytime it exceeds that threshold, overcurrent will be picked up for a definite time duration. It's 1 cycle. It can be changed to up to 60 cycles. Let's see some of the points that are available. On the left-hand side of the screenshot here are the inputs, and on the right are the outputs. These are the list of the points that are available. I'm just showing the volts from 2 buses and 3 amps from bus 1. And similarly, the outputs are here, such as reset energy, reset demand parameters. You would see some of the digital outputs here that are for future use cases. So it's very simple to configure NCD. Feel free to give us a call if you need help with NCD configuration. Now let's take a look at how do we order it. Most of the audience are familiar how to use the coding card, but for example, if you need to order an OrionMX with 2S expansion case and 2 M1 meter cards, with 6 split core CTs. This image kind of shows this. If this is the box that you need, you can go to our coding card website, select the OrionMX, and then 2S, so that can accommodate two expansion cards. And then from there, you would choose AC meter card on slot A, M1, and M1. It doesn't have to be M1, M1. You can select the aux meter card too. But for our example, we're showing 2 M1 cards in the 2S slots. And then we would choose the split core CTs, which was 6 of them. What we've chosen is 25 feet cable. For those of the application requires longer length, you can choose a 50 feet cable, the bottom option here, and you can select 6. It's very easy to configure the part number. Next we have is our customer community site. It's very handy. It can be reached at novatechautomation.com/community. This gives you access to the current power hour or previous recorded power hours, stuff like drawings, user manual, tech notes, and data sheets. All of that can be accessed by the community website. You would need to log in, and then you should be able to access all of this information. Also, we have our support site. This gives you access to the firmware for our Orion, Biotronics, and Kronos firmware, some of the release notes. You can also exchange files over large files over my files. So that's also a good website to keep on. Last but not the least, you can book some time with the sales engineer. Some of the sales engineer at the bottom right, you can see you can select any one of them, select the date and time and the time of your choice, give us a brief description of your issue. We should be able to book a Teams call and help you out. With that being said, that's all we had. Thanks everyone, and we can see if there are any questions in the chat.
This is Ray Wright speaking. We did have a question about the maximum allowable distance between the clamp-on CT and the Orion MX. That's 50 feet. There's 2 choices, either 25 feet or 50 feet. We had another question about peak fault currents. We have the ability to record peak fault currents, but it's currently clamped at a lower level, and we're checking that out in firmware. But in the near future, you'll be able to record peak fault amps up to 12,000 amps. That's in progress. We didn't want to present that because, again, that's still being worked on. There's a couple other questions that I'd like to research, and we'll provide an answer to those in the follow-up email. Thank you.
Thanks, Ray. There was a question on recording the webinar. So we do record our power hours. That does go to our community website. So for those of you need to access for future use, feel free to go to our website, and this should be posted by next week, I assume. Okay, well, thanks everyone for joining our Power Hour. Enjoy the rest of your week. Thanks very much.
Thank you, Saurabh.